Tesla has grown rapidly over the past decade, when it became the first American automotive company to go public since Ford in 1956. The attraction towards Tesla is undeniable. Their cars are slick, their acceleration is insane, and perhaps most importantly, their brand represents a movement towards renewable energy. Tesla has attracted thousands of well-intentioned people who want to play their part in saving the world. But there have been niggling questions on the minds of many EV owners and EV naysayers. When is that expensive battery going to need to be replaced, and at what cost? As existing Teslas begin to age and more exotic and demanding models of Teslas come to the fore, like the Tesla Truck and Roadster 2, these issues are going to become more prominent. These batteries do not come cheap, but they are getting cheaper. This chart shows the cost per kilowatt hour for Tesla's power packs and the market average, both dropping dramatically as technologies advanced and manufacturing volumes increased. But that storage capacity slowly creeps away as the battery is used, slowly degrading the range of your electric vehicle. Tesla currently offers a warranty to all Model 3 owners that covered below 8 years or 160,000 kilometers, whichever comes first, guaranteeing a retention of capacity of at least 70% when used under normal use. If it falls below that, they will replace your battery for free. Finding out what is considered normal use is pretty difficult, but they seem to be reasonable with it going by customer satisfaction reports. From our graph earlier, it's estimated that Tesla is achieving a cost of $150 per kilowatt hour of battery packs. So the 50 kilowatt hour battery pack of the base model would cost around $7,500 to replace. So they must be pretty confident on those numbers, as a massive recall of the approximately 193,000 Model 3s currently shipped would ruin Tesla. Ultimately, these batteries are unlikely to drop below the warranty's guarantee in those 160,000 kilometers. But even so, improving batteries is obviously just a wise business decision to retain those customers in future. This is just one of a myriad of factors that influenced Tesla's recent landmark acquisition of Maxwell Technologies for $218 million. A rare Tesla acquisition that sets Tesla up for not just cheaper batteries, but better batteries that will be lighter, have greater range, and live a longer life. It wouldn't be the first time an automotive company underestimated their battery degradation. When the Nissan Leaf debuted in 2010, the battery production they needed simply did not exist, and neither did the technical expertise required to design battery packs. In those days, lithium-ion batteries cost about $400 per kilowatt hour for laptop-grade batteries, and up to $1,000 per kilowatt hour for the ones with the longevity needed for an electric vehicle. To minimize cost, Nissan decided to start production of their own batteries and opted for a small 24 kilowatt hour battery, giving it a range of just over 100 kilometers, suitable for city driving, and that's about it. But customers soon realized that this paltry range was dwindling quickly. With just 1 to 2 years of driving, the Leaf's battery capacity was dropping up to 27.5% under normal use. Despite careful in-house testing, Nissan overlooked some crucial test conditions when developing their battery, and because of this, they made some crucial design errors. To learn why this degradation happens, we first need to understand how lithium-ion batteries work. A lithium-ion battery, like all batteries, contains a positive electrode, the anode, and a negative electrode, the cathode, separated by an electrolyte. Batteries power devices by transporting positively charged ions between the anode and cathode, creating an electric potential between the two sides of the battery and forcing electrons to travel through the device it is powering to equalize the electric potential. Critically, this process is reversible for lithium-ion batteries, as the lithium ions are held loosely, sitting into spaces in the anode and cathode's crystal structure. This is called intercalation. So, when the opposite electric potential is applied to the battery, it will force the lithium ions to transport back across the electrolyte bridge and lodge themselves in the anode once again. This process determines a huge amount of the energy storage capabilities of the battery. Lithium is a fantastic material for batteries. With an atomic number of 3, it is the third lightest element and the lightest of the metals, allowing its ions to provide fantastic energy to weight characteristics for any battery. But the energy capacity of the battery is not determined by this. It is determined by how many lithium ions can fit into these spaces in the anode and cathode. For example, the graphite anode requires 6 carbon atoms to store a single lithium ion to form this molecule. This gives a theoretical maximum battery capacity of 372 mAh per gram. Silicon, however, can do better. A single silicon atom can bind 4.4 lithium ions, giving it a theoretical maximum battery capacity of 4,200 mAh per gram. This seems great and can provide increases in battery capacity, but it also comes with drawbacks, as those 4.4 lithium ions lodging themselves into the silicon crystal lattice causes a volume expansion of 400% when charging from empty to full. This expansion creates stress within the battery that damages the anode material that will eventually destroy the battery's capacity over repeated cycles. Battery designers are constantly looking for ways to maximize this energy density of their batteries while not sacrificing longevity of the battery. So what exactly is being damaged in the batteries that causes them to slowly wither away? When researchers began investigating what caused the Nissan Leaf's rapid battery degradation, they began by opening the battery and unrolling the battery's contents. They found that the electrode coatings had become coarse over their life. Clearly, a non-reversible reaction was occurring within the cell, but the change was expected. In fact, the chemical process that caused it is vital to the operation of the battery. When a battery is charged for the very first time, a chemical reaction occurs at the electrolyte-electrode interface, where electrons and ions combine. This causes the formation of a new layer between the electrode and electrolyte called the solid electrolyte interface. The name is exactly what it suggests. It's a layer formed by the liquid electrolyte reacting with electrons to form a solid layer. Thankfully, this layer is permeable to ions, but not electrons. So it initially forms a protective layer over the electrode that allows ions to enter and insert themselves via intercalation. But it is impermeable to electrons, preventing further reaction with the electrolyte. At least that's the idea under normal conditions. The problem is, under certain conditions, this layer can grow beyond just a thin layer of protective coating and result in the permanent lodgement of the lithium that provides the battery with its energy storage. This process is not entirely well understood and is outside the scope of this video, but we can identify some of the factors that increase the rate of this formation. The expansion of the silicon electrode battery we mentioned earlier causes the fracture of the SEI layer, exposing fresh layers of electrode to react with the electrolyte. Charging rate and temperature can also accelerate the thickening of this layer. NASA performed their own in-depth study of this effect and released a report in 2008 titled Guidelines on Lithium-Ion Battery Use in Space Applications, sharing their findings. The temperature that the battery is charged and discharged at plays a massive role in the battery's performance. Lowering the temperature lowers chemical activity, but this is a double-edged sword. Lowering the chemical activity negatively affects the battery's ability to store energy, which is why batteries have lower ranges in cold countries. But lowering the chemical activity also decreases the formation rate of that SEI layer. This is one of the reasons the Nissan Leaf's battery lost a huge amount of capacity over just 2 years in many countries. Nissan performed most of its testing in stable laboratory conditions, not over a range of possible temperatures. Because of this, they failed to realize the disastrous effect temperature would have on the life of the battery, and failed to include thermal management system, which is commonplace in any Tesla. And this of course reduces the energy density of the battery. Adding tubing, the glycol needed to exchange heat, along with the heat pumps and valves needed to make a thermal management system, not only adds weight, but it draws energy from the battery to operate. But it plays a vital part in maintaining the performance of the battery. Nissan's choice to not include a thermal management system, even in the 2019 version, makes it a poor choice for anyone living in anything but a temperate climate. Of course, just cycling the battery through its charged and discharged states is one of the biggest factors in degrading the battery. Every time you cycle the battery, you are giving the SEI layer opportunities to grow. Minimizing the number of times a cell is cycled will increase its life, and maintaining an ideal charge and discharge voltage of about 4 volts minimizes any resistive heating that may cause an increase in chemical activity. This is where Maxwell Technologies comes into play. Maxwell has two primary technologies that Tesla will be taking advantage of. The first is what Maxwell are known for, their ultracapacitors. Ultracapacitors serve the same fundamental job as batteries, to store energy, but they function in an entirely different way and are used for entirely different purposes. The fundamental difference between a capacitor and a battery is that a battery stores energy through chemical reactions. As we saw for lithium-ion batteries earlier, this is done through insertion into the crystal lattice. Capacitors instead store their energy by ions clinging onto the surface of the electrode. This is a standard ultracapacitor schematic. On each side we have an aluminium current collector with thin graphite electrodes on each, separated by an electrolyte and an insulating separator to prevent the passage of electrons. In an uncharged state, ions float in the electrolyte. When a voltage is applied during charging, ions drift towards their opposite charge and cling to the surface, holding the charge in place. When a device is connected to the capacitor, this charge can leave quickly, while the ions drift back into the electrolyte. The key limiting factor for ultracapacitors is the surface area available for this to happen, and nanotechnology has allowed for amazing advances in the field. This is what the inside of an ultracapacitor looks like. It contains hundreds of layers of these electrode pairs. But even with this enormous surface area, ultracapacitors simply cannot compete with batteries when it comes to energy density. Even Maxwell's best ultracapacitors have an energy density of just 7.4 watt-hours per kilogram, while the best guess for Tesla's current energy density is about 250 watt-hours per kilogram. Counter to what corporate-owned tech channels may tell you, ultracapacitors are not intended to be a replacement for batteries. They are intended to work in conjunction with batteries. Ultracapacitor strength is their ability to quickly charge and discharge without being worn down. This makes them a great buffer to place between the motors and the battery. Their high discharge rate will allow them to give surges of electricity to the motors when rapid acceleration is needed and allow them to charge quickly when braking, saving the battery from unnecessary cycles and boosting its ability to quickly provide current when needed for acceleration. This is going to be a massively important technology for two upcoming Tesla vehicles. The Tesla Roadster 2, which will boast an acceleration of 0 to 60 in just 1.9 seconds, which a normal battery would struggle to achieve the discharge rate needed without damaging itself. The second vehicle is the Tesla Truck. I have made a video in the past noting that the Tesla Truck is going to be limited in its range and cargo hauling ability as a result of the heavy batteries it will need, as trucks are limited in weight to about 40 metric tons in most countries. This ultracapacitor technology will boost its ability to regain energy from braking significantly, and thus allow its battery capacity to decrease, in turn allowing the truck to swap batteries for cargo. The second technology Maxwell has been touting as their next big breakthrough is dry-coated batteries. This is a manufacturing advancement that Maxwell claims will reduce the cost of manufacturing, a factor Tesla has been working fervently to minimize with the growth of the Gigafactory. So, what are dry-coated batteries? Currently, in order to coat their current collectors with the electrode material, Tesla, in partnership with Panasonic's patented technology, must first dissolve the electrode material in a solvent which is then spread over the current collector. Both are then passed through an oven for drying, where the solvent evaporates, leaving just the electrode material behind. This adds cost to the manufacturing procedure as the solvent is lost in the process, and the baking process takes energy. On top of this, the solvent is toxic, so removing it from the process would benefit the environment. Maxwell instead uses a binding agent and a conductive agent, which I assume will work similarly to electrostatic painting, where a metal being painted will be given a negative charge, while the paint will be given a positive charge as it is sprayed, attracting it to the metal where it will cling to it. This painting process also eliminates the solvents needed in the paint. In this paper, published by Maxwell Technologies, they detail how their dry coating manufacturing techniques could result in a higher energy storage capacity of the electrodes due to a denser and thicker coating, resulting in a potential increase in battery capacity to 300 watt-hours per kilogram, 20% up from our best estimates of Tesla's current specs. Only time will tell if this claim can be realized at an industrial scale. Perhaps more importantly to Tesla, they now own this manufacturing technique. Currently, Panasonic owns the manufacturing process for Tesla. There is literally a line of demarcation in the Gigafactory separating Panasonic and Tesla. denoting the point at which the ownership of batteries transfers hands. Having to buy their batteries from Panasonic adds cost that Tesla will want to avoid in future, and this step could allow for full vertical integration of their battery manufacturing, thereby making electronic vehicles more affordable to the everyday consumer. As always, thanks for watching, and thank you to all my Patreon supporters. If you'd like to see more from me, the links to my Instagram,